like to encourage anybody who's listening in, if they have questions during the talk, just to break in and answer, that would be fine. Otherwise, we'll have time for discussion at the end of the talk. You'll see the title, Longitudinal Analysis 1. As I said, I'll start this week and then continue the topic next week. You see my name there. There's one suggested textbook, Applied Longitudinal Analysis. The topic, while it's not new, is relatively new, and so it's still difficult in a way to get the material in an accessible, readable way. This is probably the best that's out there, so if you're looking for sort of backup information, this is a good way to find it. And what I'm going to be doing today is talking mostly about study design and concepts. Next week we'll switch over to the actual analysis. So particularly just the notion of independent versus dependent outcomes, different sorts of study designs that could lead to dependent outcomes, and therefore the types of analyses we're going to talk about next week. A subtle but important distinction within subject effects versus between subject effects. I'll try to describe them first in words and second through an example. The example involves CD4 counts measured over time, baseline 6 months, 12 months in individuals. I'll be using that example this week to show you the ideas and also some results, and then I'll use it again next week when it comes to actually the different methods for analysis. Reason for splitting the talk between design and methods. Unlike ordinary analyses, t-tests, or even linear regression, when it comes to repeated measures, correlated outcomes, there are unfortunately many approaches that often lead to similar but not identical answers. And so the analysis is not as straightforward as one would hope. So we'll start with ideas first and then analyses next week. And then part of design is going to be sample size. So when you're designing a study, it's not only recognizing that you'll have correlated outcomes, anticipating how that correlation will affect your answers, but also it's going to affect the sample size that you need in order to do the study. So that topic is also embedded in today's talk. Okay, so terminology. Dependence is the word that I'm going to use most commonly, and so conceptually, two measurements are said to be dependent if knowing one of them gives you some information about what the value of the other might be. So definitely not a technical definition. But for example, if I told you my blood pressure, if I measured it and told it to you right now and measured it again an hour from now, does the first reading give you any information about what the second one might be? Hopefully your answer will be yes, and then we can say that blood pressures serially measured are dependent, and so our analysis, our sample size calculations all need to deal with dependent data. If I told you that I was going to measure my blood pressure and then go over to the office next door, measure my colleague's blood pressure, does my blood pressure tell you anything about my colleague's blood pressure? Your answer hopefully would be no. Those two measurements are not dependent, and so from different individuals, blood pressures are not dependent, they're independent, but two blood pressures from the same person would be dependent measurements. So that's the notion, just knowing one value tells you a little bit something about the next reading. Other words that people use to measurements are associated with each other. If they're associated, they're dependent. One can be predicted from the other, or one is correlated with the other. And correlation also goes with another statistical term, covariance. We're not going to worry about the distinction between the two, but correlation is proportional to covariance. And so sometimes if you're reading, you'll see one covariance, other times you'll see the other term, correlation. Those have particular statistical definitions. Conceptually, all these words, dependent, associated, predictable, correlated all mean essentially the same thing. So that's the starting point. However, there are different types of dependence, and so it's important, since you've probably heard about many of these already, to know which one we're going to focus on, because again, it's an easy way to get confused early on. So if we have a study and there's a predictor that you're interested in to see if it's related to an outcome, you're interested whether that predictor, whether the outcome is dependent on the predictor or whether they're independent of each other. That's a type of dependence. It's the type of dependence you investigated in an introductory biostatistics course. It's clearly important. That's what a t-test is trying to tell you. It's trying to measure dependence through a chi-square test. That's essential, but it's not what we're going to talk about today or next week. So that is certainly a type of dependence. We have a hypothesis that there is no dependence between them. The outcome and predictor are independent, and we want to see if the data tells us differently, but it's just not the topic for today. Another type of dependence would have come up if you took a second level biostatistics course in regression. There you have an outcome variable, but you probably have multiple competing predictors. If those predictors are related to each other, dependent on each other, then they could cause confounding, they could cause collinearity, and when you build your regression model, you have to build it carefully to include confounders and avoid collinearity. So dependence between predictors is a very important topic, but hopefully one that you covered in the second level regression course. What we're going to talk about today basically comes out in third level courses, where we have dependence between outcomes. So number one, dependence between predictor and outcome. There's a t-test. Dependence between competing predictors is a linear logistic regression issue. But when you have multiple outcomes on the same person or from the same entity and they might be dependent, that's the type of dependence that we're focusing on in today's lecture. So dependence between outcomes. So a regression model where you have dependent outcomes, or if you want to say a regression model with correlated outcomes, is called a multivariate analysis. So those three are synonyms. Sometimes people are presented mistakenly multivariate analyses as regression models with multiple predictors. Technically, that's a multivariable, BLE analysis. Technically, it's not a multivariate analysis, although people interchange those terms. The technically correct use of multivariate is when there are dependent outcomes. Again, my example will be every patient in the study has 3 measurements of the CD4 count, baseline, 6 months, 12 months. Because each patient has 3 dependent outcomes, it's a multivariate analysis. If it was simply one outcome at 12 months and multiple predictors, that would be a multivariable analysis. Sometimes reviewers for papers care about the distinction. Most of the time they don't. But for us, since it's a new topic, I'll be particular and call this the multivariate analysis. There are different types of studies that lead to a multivariate analysis. Probably the most common is the one that I'm going to focus on today. It's a longitudinal analysis, a repeated measures analysis, or panel data. They're all not identical, but very close to each other, and I doubt that most people know or care about the distinction. The one example that I'm going to go through today, again, CD4 count at month 0, month 6, month 12, that's the no-show longitudinal data. The same patient is measured 3 times, that's longitudinal. The CD4 count is measured repeatedly, so repeated measures. The patient is the panel. We have 3 measurements for the patient. We have multiple patients. The patients are the panel. each panel member has 3 measurements. So all of those are close to synonymous at least, and that's where we'll focus, so that's what I'll get to last. Another sort of study design that leads to a multivariate analysis would be clustered data or multi-level data or hierarchical data. And I'll give you an example of that on the next slide, so I won't try to explain it without some words in front of me. The form of the database will be the same. The choices for analysis next week will be the same. But it's just the structure of the study, and you'll see in a slide what that means. There's also the notion of classic time series, where instead of many patients multiplied measured 3 or 4 times each, you have basically one long series where the same thing, a blood pressure can be measured 100 times every minute for 100 minutes, but you only have one patient. Or more likely, you'll have things like tuberculosis incidents over the last century. It's one long series, and you'd analyze it using classic time series. Again, I'll give you a slide showing examples and some words. For classic time series, the analyses are quite different. We're not going to have time to talk about them. They're not as common and so not as useful, and so that's where we're not going to spend the time. And then there's one other classic approach, classic multivariate analysis of variance, or MANOVA. I expect that many of you have heard ANOVA. This just puts the M in front of the ANOVA. It's a related idea, and again, I'll explain it on a slide. It'll be easier there than without some backup words. So these are the classic multivariate analyses. The first is where we'll concentrate. The 3 latter bullets I'll deal with quickly right now. So cluster design, we're measuring the outcome, let's say an outcome for each patient in our study. Something simple, whether the patient lives or dies. More complicated, continuous, the patient's quality of life. And we're going to measure it once for each patient. That patient will be our unit of analysis. That's an important phrase. And so if you're trying to explain in your method section what your study looks like, what the analysis will be, your readers will want to know what's the unit of analysis, and it'll be the patient. But the concern comes in when 2 patients are seen by, for example, the same physician. Those 2 patients are more likely to have similar outcomes than patients seen by different physicians. I'm hypothesizing that. I don't know it for a fact, but I think that the outcomes are driven by the quality of care that the physician gives. And if we switch to a totally different outcome, patient satisfaction, then almost certainly 2 patients seen by the same physician, their satisfaction ratings will be much more similar to each other than a patient seeing physician A and a different patient seeing physician B. So patients seen by the same physician fall into the same cluster. And so while the patient is the unit of analysis, physicians constitute clusters. And we talk about patients being nested within physicians. So as you can see, there's an entire language built around this sort of study design. And then it can certainly get more complicated. So 2 physicians who work in the same clinic are more likely to have similar outcomes than physicians seen in different clinics, either because of the resources available in the clinic, because of the way that physicians are trained in that clinic. And so, in fact, clinics can also be considered higher level clusters. And so patients are nested within physicians, and physicians are nested within clinics. Clinics can be nested within hospitals. Hospitals are nested within health systems. And so this is now getting into what I called previously multi-level data, patient to physician, to clinic, to hospital. And there's clearly a hierarchy. So, interesting sorts of studies. If you do any sorts of health services research to see how the health system functions, outcomes very often are measured at the patient level, but they're influenced by many of the higher level clusters. And so the patient outcomes are dependent on each other if the patients are seen by the same physician. Patient outcomes may be dependent on each other if they're seen by within the same clinic. And so we have dependent outcomes, even though each patient only has one outcome. Their outcomes are related to other patients seen by the same physicians or clinics or hospitals. It's a very interesting design, very useful. The analyses actually match perfectly well to what we're going to talk about next week. But we're going to sort of keep things simpler this week by not going any further with cluster designs, unless you have questions you want to pursue. And we're going to switch from cluster designs momentarily to classic time series. And then MANOVA, and finally our topic for the week, longitudinal analysis. So classic time series, we have one very long series of many repeated measurements, so daily measurements of temperature over 10 years. There's only one series. Temperature today depends on what the temperature was yesterday, may depend on what it was the day before, and tomorrow's temperature will depend on today. So our outcome measurements are dependent from one to the next. The degree of the dependence depends on how far apart they are, and those temperatures can depend on a large number of predictors. So we're still going to put together a regression model, and the outcomes will be dependent, but the style of the study, one long series, makes it into what we call a classic time series. ARIMA models, if you have any familiarity with the topic, that's the usual approach to the analysis. Very different than the analysis we're going to talk about next week, though. If you want something more medical, the early incidence of tuberculosis over the last century. Again, the number of cases will depend from 1 year to the next. They can be influenced by a lot of different predictors. And so again, we have a dependent series of outcome measurements, and the analysis folds into basically a set of approaches very different from what we're going to talk about this week or next week. And just to contrast it, what we're going to talk about this week, the longitudinal or repeated measures, we have many short series of a few repeated measurements each. So instead of daily measurements of temperature over 10 years, we're going to have CD4 count at time 1, 2, and 3. But we'll have it not just with 3 time points, but we'll have it over many, many patients. So not one very long series, but many short series. And short doesn't have to be 3, it can be 5 or 10 or 20. But typically, it's a lot less than temperatures over 10 years. The other classic study design, MANOVA, is very rarely used. I'll say why at the bottom of this slide. The analysis approach, though, was available and has been for decades. The idea here, though, is for each subject we measure K different outcomes, so 3 different outcomes for each subject, and compare those outcomes between groups of subjects. So if we go to the next bullet, let's say we measure 3 outcomes for each patient from echocardiography, heart mass, wall thickness, and contractility. And we want to know if men's hearts are different than women's hearts based on those 3 numbers. So this is not heart mass when they're an adolescent, when they're middle age, and when they're old. It's not the same number 3 times over time. It's 3 numbers, heart mass, wall thickness, and contractility, different units, different measurements, all measured at the same time, and all related to each other. So the thicker the walls, the heavier the mass, it'll affect the contractility. So we have 3 outcomes per subject, and they are dependent with each other, and we want to analyze them all 3 at the same time. So not doing a t-test comparing heart mass between men and women, and then doing wall thickness between men and women, but we want all three of them at once, saying, is there any sort of difference between the hearts of men and women when it comes to those three measurements? What you'll end up with the MANOVA is a single p-value, a single test, comparing women's hearts to men's hearts, saying that they're different or not. The trouble with the approach is if the test is significant, you won't know what aspect of the heart was different, and then you want to go and compare heart mass between men and women, thickness and contractility all separately, and whatever the MANOVA told you originally becomes lost because it combined things that you wanted to know about separately. And if the test comes out non-significant, you're usually unhappy because it doesn't mean the heart mass didn't differ. It just means the combination of the three didn't differ, and so you still end up going and comparing heart mass between men and women. So MANOVA is possible, single test comparing all three between men and women, but the answer usually is not satisfactory from the clinical perspective, and so you rarely see the MANOVA used. And finally, where we're going to spend the rest of the lecture today as well as next week, longitudinal analysis. So I'll interrupt myself briefly to give you a chance to ask questions.
Any questions? Okay. Feel free.
Okay.
All right, so no question. It's very clear so far. Thank you.
Good. Okay. So this is probably the easiest conceptually, a longitudinal analysis. We measure the same thing for each subject over time, and we can do any of three things. See how that measurement changes over time, and that would be called a within-subject effect. So even if you had one person, you could look to see how their CD4 count changed over time, and so it's a within-subject change or within-subject effect. Or we could take this data and compare subject characteristics which influence the outcome. So are CD4 counts for men different than CD4 counts for women? Because in our study, we might have baseline 6 months and 12 months, but some of the people we measured were men, some were women. We can compare CD4 counts between men and women, and that's a between subject effect. And then finally, we can combine the two ideas. So is the pattern of change for men over time different than the pattern of change over time for women? So maybe for men, CD4 counts are stable. For women, CD4 counts are going up. So we're looking for a between subject time interaction effect. So we're combining both the within subject, the time progression, with a between subject, looking for whether the progression is different between men and women. So within subject effects, between subject effects, and then the combination, the interaction or effect modification of the two. Your study may only be interested in with time progression. That's fine. It may only be interested in comparing intervention and control between subjects. That's fine. Or you may be interested in both. That's fine as well. So into the eventual regression model, I'll show you the models shortly, you can look to see how any of these are changing. So there's ultimate flexibility, just like in a regular regression, except now there's also this notion of change over time. So the example makes it a little bit easier to understand. So we have three measurements for each subject. Have the CD4 counts changed over time? Are CD4 counts different between men and women? And is the pattern of change over time different between men and women? Initially, I'll show you models for all three of them and the results. These are real data. They're relatively old data, but they are real data. And then we're going to spend most of the rest of the lecture focusing in more on 1 and 2. 3 is just complicated. If you've had a regression course and you've had to deal with effect modification, you'll know why I say it's complicated. It just is, whether it's in the context of longitudinal or any other model. So we'll keep it mostly simple, but just to prove that it can be done, I'll show you an example of each. So we're going to enroll a cohort of subjects, record their age and sex, evaluate each subject and measure their CD4 count at baseline. I'll call that time 0, 6 months, time 1, and again at 12 months, time 2. And then I'm going to use a longitudinal linear regression model. Linear because CD4 counts are continuous. They should be normally distributed if I'm going to run a linear regression. I did look at the distribution. It does look relatively normal, and I'm asking you to trust me on that. I'll show you more of the data next week when it comes to choosing the analysis. But for now, just to stay with sort of the structure of the data, assume that continuous and normal will hold. Each subject clearly has multiple outcomes, 3. I should mention now, though, not every subject has 3. The design of the study was to have 3 measurements. Everybody enrolled, so everybody has a time 0. Some people miss their 6-month appointment. Some people miss their 12-month appointment. Some people die and don't have 6 or 12. That's all okay as far as the analysis goes. And so having missing data, a gap for a particular patient, is not fatal in any way to this analysis. There are 101 subjects. I do not have 303 measurements. That's okay. Everything will make sense. The program will run regardless. So in the old days, you needed complete data. And very often the analysis would actually drop people who didn't have complete data, which would introduce a bias. Now the software will use whatever data are available for whatever subjects you have. So time and sex I'll take as my main effects predictors. Time is a within subject predictor. Sex is between subjects. And then I'll have an interaction, time by sex, to see whether time trends are the same for men and women. That's what my data look like, or at least this is the easiest way to conceptualize them. CD4 counts are on the y-axis. Time 0, 1, and 2, or time 0, 6, and 12. Baseline 6 months and 12 months. Those are the CD4 counts, the dot for each patient. I think you can see sort of the general pattern that CD4 counts are going up with time. I don't remember if I even mentioned that these patients have HIV. They're in a treatment program, and so you would expect the CD4 counts to be going up. What's lost in this particular version of the presentation is the fact that these are the same patients at month 0, 6, and 12. For all you know, if I hadn't given you the background, at time 0, those could be a group of patients diagnosed, have their CD4 counts measured. At time 6, it could be an entirely different cohort of patients who were diagnosed 6 months ago and now have their CD4 counts. And for all you know, at 12, it could be an entirely different third cohort with CD4 counts measured. And so the next picture is actually the more accurate one. Spaghetti plot, if you like that term, but it gives you the correct impression of what's going on, although it's complicated. You see the dots are now connected, so you can see what happened to an individual patient. And you can see the patient on top in red had very good progression from 800 to over 1400 in their CD4 counts. If you trace some of the other lines, there were patients certainly who were stable, even some patients who went down, the bottom triangle in green. But this is a much better conceptual representation of the data. I'm not sure I would suggest putting it in a journal, but in terms of learning, this is really the data that we're attacking today. These are 101 people, some with 2, some with 3 measurements, but everyone has basically a pattern, and we want to see, is that pattern generally going up or not? And the usual, This is the results of the regression. Men and women clearly don't have very much difference. Females are red line, males are the blue line. I kept my model simple for no other reason than simplicity, and put a straight line regression, so a slope. The slope for men is not very different than the slope for women, and there's not much separation between them. So the progression that we're seeing over time seems to be fairly consistent between men and women. That's the pictorial presentation. Here's the actual model, and so I guess I'm asking you to remember your basic regression, your basic linear regression. If that's not familiar, then proceeding is going to be a problem. As I said, longitudinal modeling is a third level course. You need the basic ideas of biostatistic, you need the basic ideas of regression, and then we can add on this topic of dependent data. So, assuming independence, which I know is wrong in this case, the model would be Y, which really is CD4 count. So I wrote it as a Y here, but just translated. That's the CD4 count that I measured. Model intercept, beta 1 times time plus beta 2 times sex. These are my main effects. I'll show you the model with the interaction in a few minutes. Time is coded 0, 1, and 2. Sex is coded 0 and 1, 0 for males, 1 for females. And when I ran this as an ordinary regression, this is the result that came out. The intercept, the alpha is 494. Since time is coded 0, 1, 2, sex is coded 0, 1. The 494 would be the average CD4 count at baseline for men, the reference group. 17.6 times time means that for every, time is coded 0612, my mistake. For every 1 unit increment in time, every month, CD4 goes up by 17.6. Standard error is there, and so there's a significant rise in the CD4 count over time. And the difference between men and women is 10. It's a small difference, which is why it wasn't visible on the graph. Has a standard error of 54 and is non-significant. And so men and women essentially have parallel patterns according to this model. Both have an increasing CD4 count of 17.6 over time. The trick, though, is that this was your standard linear regression model, which assumes that these error terms are independent from one measurement to another. Since each patient has 3 measurements, we can expect that they are not independent one to the next. And so what I should have run is what looks to be a more complicated model. This part, the double subscript, is necessary if you're going to read a textbook, an article where they actually spell out the model. Double subscript I refers to the subject. In this study, there were 101 people, so I goes from person 1 to person 101. J refers to time. Time is either 0, 6, or 12. And so for each CD4 count, it's measured for a particular person at a particular time. The subscript is inescapable. But fortunately, you don't really need to worry about writing down the model as long as you sort of understand the jump from the previous model to this model. We're going to interpret things pretty much the same. The CD4 count for the first person at time 0 is intercept plus beta 1 times time 0, which is 0. Times the gender of that person, which is not going to change over time. And so when I run this, the model looks remarkably familiar. And that's the beauty. Once you understand a little bit of background, the result you get is going to look almost identical to the result from a standard regression. The numbers will change. because this time I allowed for the error terms to be dependent. And so the intercept, the average CD4 count for men at baseline is 500 instead of 494, a slight change in the estimate. The increase over time is 17.3 instead of 17.6. Difference between men and women is 16 rather than 10. The change over time is still significant. The difference between men and women is still non-significant. If I just gave you a printout with this set of results and told you that the analysis took care of the correlation, I think you could do the rest, interpreting the model, with nothing more than you learned in your ordinary regression course. And that's sort of the beauty of it. If we can set up the analysis correctly, if we can use the right software program, the results will look very familiar. Coefficients, standard errors leading to p-values, or leading to confidence intervals in the usual way. So that's the beauty of it. Once you get through the concepts, the results look and are interpreted in exactly the same way. So I did mention that I would show you what happens if you put in the interaction here. The model actually allows for men and women to have different slopes. As you can see, the slopes are no longer identical. They cross, but they are very similar to each other. And so again, assuming independence, I ran the model with the interaction term that allows for men and women to have different slopes. And so for men, the slope is 17.4. For women, the slope is 3.3 cells higher per month. Total, I guess, is 20.7. The difference, though, between the slopes of men and women is non-significant. And so again, analytically, we can go back to the simpler model. This assumes independence, which again is wrong. When I allow for the dependence of CD4 counts within the person, the results change, but they don't change in first any way that requires you to interpret the results differently. If you could interpret a model, regression model with effect modification in your previous course, you can interpret it here. Of course, if you couldn't do it then, it's not getting any easier. The p-values, the effect estimate, standard errors change a bit, but effectively it's the same presentation. And so if you're comfortable with the regression, you'll still be comfortable with the final results of the models. Now, assumptions when we allow for dependence. The CD4 counts are normally distributed. If that's not true, we can still call on the central limit theorem, but we don't have too many other alternatives to drop back on. CD4 counts are independent from one person to another. So if I was in the study and you were in the study, my CD4 count would not tell anyone anything about your CD4 count. But my CD4 counts are dependent over time. So if I told you my baseline CD4 count and it was high, you could probably guess that my 6-month CD4 count would be relatively high. If my baseline CD4 count was low, then you could guess that my follow-up 6 and 12-month CD4 counts would be low. So dependence over time, but independence over subjects. This is the typical setup for a longitudinal analysis or panel data. So independence across the panel members, but dependence within the panel over time. So your responsibility, design the study so that you anticipate that there will be dependence over time. You'll have to increase the sample size in a way that I'll show you in a few minutes to take count of the dependence so you have sufficient power at the end. Use an analysis that takes account of the dependence, and actually before you do that analysis, organize the database so that there is a variable that identifies which outcomes are linked. So basically it's going to be the subject ID, and I'll show you a concrete example of that again before we end this lecture. So this is it. Sample size, make sure that you account for the correlation. It usually means you're going to have a larger sample size than if you had independent data. make sure that when you do your analysis, you take account of the dependence, and then organize your database so that your analysis program sees which measurements are dependent or linked together. So, as I mentioned earlier, correlation, association, dependence are all used interchangeably. Correlation has a formal statistical definition. If both variables are normally distributed, then dependence, correlation, variables being associated, two variables in order to be associated have zero correlation for normal data. Those are the same thing. So zero correlation, no association. If the data aren't normal, then you can have zero correlation, but you can still have association. For now, we're assuming the data are normal, so zero correlation, no dependence, no association are synonymous. The correlation, I'm not going to go through the formal definition, but it's a number. It measures the strength of the association. It's normalized, so it's always less than or equal to 1 and greater or equal to -1. Values of the correlation close to +1 or -1 indicate a strong relationship. Value of 0 indicates no association. You can calculate the correlation between two measurements, test whether the correlation is 0 or not. You can put a confidence interval around the correlation coefficient. If the data are normal, Pearson correlation is what you generally use. Not normal, with outliers, generally Spearman correlation. Hopefully, again, this is a very quick review of a notion that you had from a prior course. The closer the correlation is to ±1, that's the important idea for today, the more dependent the two measurements are, the more precisely one measurement can be predicted from the other. If you look at the scatter plot between the two measurements, if we have a correlation that's close to +1 or -1, the points in the scatter plot will line up closer to a straight line. The angle of the line doesn't affect the correlation. It's really how close the points are to the line. And so here's a scatter plot. People's baseline CD4 count plotted against their CD4 count at 6 months. The best fitting line was plotted through by the software. As you can see, there is a relationship, not surprisingly. This is a correlation of 0.53. So a moderately strong correlation. Person who has a high baseline CD4 count tends to have a high follow-up CD4 count, although that's not always true. People with low baseline CD4 counts tend to have lower follow-up CD4 counts. So it's a positive correlation of moderate strength, but at the very least, what's important, there is a correlation. And so if we're going to run a model which looks at both baseline and 6-month and eventually 12-month CD4 counts, the model has to allow for correlation between the measurements. And that will affect the answers to some degree. So typical scatter plot, typical correlation. The only thing atypical about this is it's not between predictor and outcome. It's between one outcome and another outcome for the same person. In this sort of analysis, you can estimate the effect of any between subject predictor or any within subject predictor. So as I showed you, I did run the correct analyses. Within subject, that was time. Between subject was gender. And if your analysis allows for correlation, if you're doing the analysis the correct way, and the measurements are positively correlated, which they usually are, then there's two sort of summary results. When you allow for correlation between these dependent measurements, it's going to decrease the power of any between subject predictors, but it will increase the power of within subject predictors. So I've tried to boil it down to these two summary bullets as far as what's going to happen. And so let me ask a question. You don't have to answer out loud, but if you do it in your mind, When I run the correct analysis, allowing for dependence, and I compare CD4 counts between men and women, that's a between subject predictor, what's going to happen to my power? Should be an easy answer. It's going to decrease the power. And what does that mean for my p-value for men versus women? If I'm decreasing the power, what's my p-value going to do? You should be thinking it's going to go up. If my power goes down, my p-value goes up. And so if you really are interested in designing a study comparing CD4 counts between men and women with longitudinal measurements, you better make sure you have enough men and enough women, because the correlation is going to hurt you when it comes to power. Second question, if I'm interested in the effect of time, are CD4 counts going up, going down, stable? That's a within subject predictor. I know that the measurements are positively correlated. I just saw that on the previous slide. If I have positively correlated outcomes, what's that going to do to my power? Well, that's good, actually. It's going to increase my power. And what does that mean for my p-value? It means my p-value is actually going to go down. And so if you're interested in the effects of CD4 count over time, you can actually get away with a smaller study, fewer people, because you're going to have better power using the dependence to your favor. If you're interested in both of these, then unfortunately you're going to need a larger sample size. Otherwise, you will not have the power for the between men and women difference. So just to demonstrate, if this helps cement the conceptual, the top, I ran the model the wrong way in assuming independence. Bottom, I repeated the results allowing for dependence. This is the correct way to do the analysis. The time effect was 17.6 when I did it the wrong way. Sorry, this is just a typo. The time effect is 17.3 when I do it the right way. But the standard error went from 2.7 to 2.0. And you should be saying to yourself, I always like smaller standard errors. That'll give me tighter confidence bands and lower p-values. Here, both p-values are below perceptible levels, so you can't see the benefit. But believe me, when it comes to a real study, a smaller standard error will lead to a smaller p-value, and that's desirable. So here, by doing the analysis the correct way, I actually win. I have better power, smaller standard error for discerning the time effect. However, between subjects, men versus women, difference of 10, difference of 16. Here, the standard error when I did it the wrong way was 54. When I did it the right way, the standard error went up to 77, which means my power goes down. You won't see it in the p-value because the effect changed as well, but large standard errors are never desirable. So when you do the analysis correctly, if your interest is in within subject differences, then you win. The correlation actually is to your benefit. It's better to do the analysis the right way. But if your interest is in between subject, men versus women, the correlation is going to actually hurt you. It's going to give you a bigger standard error. And so you might have to increase the sample size in order to achieve the same power. So this is sort of the critical issue in terms of designing the study. What's your primary interest, if there is a primary interest, within subjects? If so, doing the right analysis, you win. Between subjects, if that's your main interest, between subjects, your standard error will go up and you will lose. You don't have much choice nowadays. You'll have to do the right analysis. 15, 20 years ago, there wasn't software around. Some people cheated. They said there's not going to be much correlation. I'll just run it assuming independence, and then you got what you got. Nowadays, as long as the design even suggests that there might be some dependence over time, the reviewers of a journal will force you to run a software program that allows for dependence, and this is what you can expect. You'll win when it comes to within subject. You will lose when it comes to between subject. If an hour from now you forget the distinction between within and between, the good news is your software doesn't care about your memory. It'll compute the right standard errors regardless of what label within or between. So you can anticipate what the correlation will do if that helps you design the study. But when it comes to analysis, the software will adjust the standard errors correctly. And I guess this is the other main point. The effect estimates won't change much. The big difference will come in the standard errors. But since the standard errors drive confidence intervals and p-value, that's a pretty important difference. So between subject effects, if we want to compare CD4 counts between infected and non-infected subjects, your interest is between subjects. If you want to compare blood pressure medication, we're going to do serial blood pressures in an intervention group, and they receive the treatment and control patients. That's a between subject effect. And if you think back 2 slides, if I'm interested in comparing treatment effects and doing serial blood pressures, the correlation is going to hurt me. So it's going to hurt the p-values. If you're going to do within subjects, you want to see how serial CD4 counts change over time, or really look at any other predictor which changes over time. So does the presence of an infection prior to the CD4 count being measured change the CD4 count? That's also within subjects, since the infection occurs or not with each and every time point. In this case, it's a within subject effect, and the correlation will help you. So between and within, the impact itself and how it's going to play out in terms of power calculations, sample calculations, this is sort of the statement. If we're looking between subjects, compare treatment and control, compare HIV infected and non-infected, then 2 measurements on the same subject are not worth as much as 1 measurement on each of 2 subjects. So in a sense, 2 doesn't equal 2. 2 measurements on the same subject are worth less than 1 measurement on each of 2. Or another way to phrase the same thing, 2 measurements on the same subject are not worth twice as much as 1 measurement. 2 measurements on the same subject are still worth more than 1, but not twice as much as 1. And so you can think about it as, well, if I keep measuring the same person over and over again, do I win in terms of power? The answer is yes. Do I win a lot? The answer is no. It becomes a marginal gain. How much of a marginal gain depends on how correlated the measurements are. And so if we take it to the extreme, if the correlation is 1, then 2 measurements on the same person are worth no more than 1 measurement. So if I'm going to ask you what your age is, and compare ages of men to ages of women, I can do that simply with a t-test comparing the average ages of the 2 groups. If I ask you your age again on the same day, do I gain any information? Clearly not, because you're going to give me the same number. The correlation between your age this morning and your age this afternoon is 1, and so having asked you your age twice gets me nothing more than 1 measurement. It's no gain at all. But if the correlation is 0, if there's information gained by asking, then 2 measurements are worth 2 measurements. I'm gaining just as much the second time as the first time because there's no information carryover. It's new information. It's worth asking. In most cases, though, the correlation is someplace between 0 and 1, and so 2 measurements are worth not 1, but not worth quite 2. They're worth 1 point something measurements, and that depends on the correlation. If the correlation is low, getting your blood pressure twice is like 1.8 independent measurements. The correlation is higher, 2 blood pressures from the same person, are worth 1.6 independent measurements. The correlation is 0.5. 2 measurements are worth 1.3. So the higher the correlation, the less new information I gain. And if I go to 3 measurements or 4 measurements, again, the gain becomes more and more marginal. And so with a high correlation, you can do your study, design your study, measure each person 2 or 3 or 4 times. It's probably worthwhile. Measure them 5 or 6 or 10 times. You're doing a lot of measurements without a lot of gain, without much improvement in power. Your power will never go down. It just won't go up very much. And so here would be an example. We're going to do a study. We have enough resources, money for 25 subjects. I'm going to stretch my study by measuring each subject 4 times. And so if you like, there'll be 100 outcome measurements available for analysis. So is my sample size 25, which seems unfair. It seems low. But 100 seems high since it's not really 100 people. It's 4 measurements from each person, and I suspect that there's correlation between those 4 measurements. So my gain is not from 25 to 100. There's something called an effective sample size between 25 and 100. So I suspect my study is worth more than 25 in terms of power, but not quite as much as 100. The true effective sample size depends on the magnitude of the correlation. And when I do my power calculation, when I try to figure out whether this design is good or bad, I need to know the effective sample size, not the 25, not the 100, but the number in between. Now, the calculation was actually pretty straightforward. There's a definition that I can't avoid, which is the interclass correlation coefficient. It's really the correlation between your dependent outcome measurements. So when I showed you that scatter plot, and I said that the correlation between the baseline and the 6-month CD4 count was 0.53, that's the number I'm looking for here, 0.53, the correlation between those serial measurements. Once you have that correlation, and if you're designing a study, I imagine either you have pilot data or you're going to make up a number. I can calculate what's called the design effect. Design effect is just 1 plus k minus 1 times the correlation. K is the number of measurements made on each person. In my prior story, K was 4. Each person is measured 4 times, and so K is 4. In my CD4 count study, I had each person measured at baseline, 6 months, 12 months, that's 3, K is 3. And so K is not a big deal. If you're designing a study and you plan to measure each person 5 times over follow-up, K is 5. The hard number to come by is the correlation. For physiologic measurements like blood pressure, CD4 counts, measured a reasonable interval of time apart, a 0.5 is not a bad guess. If you have pilot data, that will give you something better than a raw guess. But for physiologic measurements, 0.5 is actually a pretty reasonable start for most things you measure on a person. Once I have D, the effective sample size is the total number of outcomes divided by D, and I'm done. So between these 2 slides, here is a formula for D. K is known from how you plan to design the study. Rho is going to be made up, probably to be 0.5. Then you take the total number of outcomes divided by D. I have my effective sample size, and the power of the study is based not on the total number of outcomes, not on the number of people, but on this effective sample size. And that's what I'll take you through in the next couple of slides. Here's my example, 25 subjects. Each person measured K equals 4 times. I'll assume that the correlation is the usual, roughly 0.5. D is 1 plus K minus 1, 3 times 0.5. D is 2.5, that's the design effect. Total number of measurements, 4 times 25 is 100. The effective sample size is 100. Divided by D, 2.5 is 40. My effective sample size is 40. they'll always be between 25 and 100. If the correlation were higher than 0.5, the effective sample size would have been lower than 40. If the correlation was lower, I would have gained more information. The effective sample size would have been higher, closer to 100. But right now, this study, 25 subjects measured 4 times each, is the equivalent of a study of 40 independent subjects. This is like 40 independent measurements. That's my effective sample size. And like I said, it's a fairly straightforward calculation with one guesstimate involved, the correlation. If you're curious what the implications are, I just generated some power calculations for doing a study that would have 90% power to find a half standard deviation between two groups. If I used independent measurements, I would need 84 people in each arm. So if I wanted to compare the effect of an intervention on blood pressure, measuring blood pressure once per patient, let's say at 1 year, I need 84 people in the treatment group and 84 people in the control group. Each person is measured once, so each of the 84 people leads to 84 measurements. I look at this 84 and say I don't have that many patients available to study. And so instead, what if I enrolled fewer patients but measured them twice each? If the correlation between the two measurements is low, then I could actually do this same study, still achieve 90% power, using only 44 people per group. 44 with the intervention, 44 with the control. That's a lot less than 84 people per group. But remember, you do have to measure them twice each. And so it's 88 measurements, which is more measurements, but many fewer people. So to get 90% power, each person measured once, 84 people. 44 people, but measured twice each, will get you 90% power. However, if the correlation is higher, you're not gaining as much new information. It's not 44 people, it's 46. The correlation is higher still, 52 people. Or if the correlation is 0.5, you'll need 63 people per arm, which is still better than 84 people per arm, but now each person is measured twice, and so you need 126 blood pressure measurements, 2 on each patient. 126 blood pressure measurements is not a big deal. If these were MRIs, then now it's a financial consideration. I like having fewer patients. I don't like doing this many MRIs. They become costly. So any one of these designs, this number of patients leading to this many measurements on each, will give me 90% power. You have flexibility on how you design the study. Next slide is going to 3 measurements. For the sake of time, I'll skip it. That was when I looked and compared groups of patients to each other. I also mentioned within subject effects. So if we're looking for the effect of time on CD4 counts, here I said we actually gain. And so we have almost the opposite wording. 2 measurements on the same subject are worth more than 1 measurement on 2. Or if you like, 2 measurements on the same subject are worth more than twice as much as 1 measurement. You actually get a benefit. And so if the correlation is 0, 2 just equals 2. But if the measurements are correlated, 2 measurements on the same person are worth 2.2 independent measurements, 0.25, 2.7 independent measurements. And if the correlation is 0.5, 2 measurements on the same person are worth as much as 4 independent people. This is the notion of a crossover trial. If you let the person be measured pre and post, you can save a lot in terms of sample size. Okay. And again, very quickly, an example. I could think about doing my CD4 count study in 2 different ways. The setup, the assumptions are above, but let me just focus on the important part. I could take 100 subjects at the time of diagnosis and measure them, and then the different 100 subjects who were diagnosed a year ago, and compare the CD4 counts between these 2 groups. I'll see the effective time, and with the assumptions above, I'd have 80% power with 100 subjects in the pre-group, 100 subjects in the 1-year group. However, if I took 100 subjects, measured them at the time of diagnosis, and waited for 1 year and measured the same people over again, if there was a correlation of 0.3, I'd have 92% power. So this is the gain from 80% power when I use 2 independent groups to 92% power when I measure the same people twice, taking advantage of the correlation between the measurements. Downside of the second design, the upside is the power. The downside is you have to wait a year. So you have to measure the people at diagnosis and then again at 1 year. Here you just find 100 people who were diagnosed recently, 100 people who were diagnosed a year ago, and you can do your study tomorrow. Here it's going to take a year to complete your study. So here's where we gain the power if it's a within subject effect. Okay. Study design and planning the study. You'll collect correlated outcomes. You have to take account of the correlation in your power sample size calculation. So we're talking about a longitudinal study. Tell me how many measurements you plan to collect per subject. Will it be baseline and 2 follow-ups, so K is 3, baseline and 3 follow-ups, K is 4. Tell me what K is. Guesstimate what the correlation, that row, will be, or get it from pilot data. Calculate the design effect, that D1 plus K minus 1 times the correlation. And if you're doing a sample size calculation, use your just usual software formula, calculate the necessary sample size, and then multiply it by D. So this is the penalty or the benefit you'll get from the correlation. So use your usual formula and then multiply by D. If you're going to do a power calculation, take the sample size you have available, divide it by D, and then use your usual software or textbook formula to calculate the power based on this effective sample size, not on the initial sample size. So the translation is always through that factor D. So once you've seen that value D, it's not that it's easy to get. K is easy to get, but the correlation will be a guesstimate. Once you have D, then you just adjust either the sample size by D, or you adjust the sample size by D and use a usual formula for the power. So that's how you adjust the study design. You'll also need to use software in your analysis that recognizes and adjusts for the correlation. You'll need to specify the form of the correlation matrix, which we'll talk about next lecture. You'll need to identify the variable that links the dependent outcomes from the same subject. I'll show you what that means on the next slide. It's straightforward enough conceptually once you see it. And then your software will actually do the rest. So as long as you're using software and it understands the source of the correlation, it will measure how strong the correlation is, whether it's within subject and you benefit, between subject and you're penalized, but the software will do the rest. And so again, how this gets done we'll talk about next week. The only thing left to talk about right now is the form of the database. For the CD4 counts, this is typically how the database is set up. So I have a subject, that's their baseline CD4 count, 1087 at 6 months, down to 651 at 12 months. They're 31 years old, and he was a man. Second subject is here. As I mentioned, there were 101 people, and so there would be 101 rows in this database that would be loaded into your software. What I need you to do, if you're going to analyze this, since the CD4 counts, these 3 numbers are my outcomes and they're dependent correlated, I need you to reorganize your database so it's in this longer format. And now, if you remember, JCO1 was my first subject. JCO1 shows up 3 times. If your memory's good, you'll also remember that those were the 3 CD4 counts for JCO1 at times 0, 6, and 12. So JCO1 is no longer one line of my database. JCO1 is 3 lines of my database where I know the timing for each CD4 count. The age doesn't change, nor does their gender. The link is through the subject ID. So my software program will ask which variables are correlated. Any measurement has the same subject number, JCO1. Those are dependent measurements. NDO2 was my second person. They also had 3 measurements. Here's the linkage, it's through the subject ID. And the CD4 counts are there for that person. Again, their age and gender don't change over time. So I'm going from a wide format with 101 records to a long format that has roughly 303 measurements. Once you set up this way, your software program will take care of the rest. And that's what we'll talk about next week. So just a summary, then I'll let you ask questions finally. In some studies, the outcomes you collect may not be independent of one another. So multiple outcomes on the same person over time, those are dependent. Multiple patients from the same clinic, those may be dependent. So this is my longitudinal study design. This would be my nested hierarchical clustered study design, which I didn't pursue, but the same issues pertain. If you do have a study with these sorts of dependent or correlated outcomes, it'll affect your results. Mainly, it'll affect the standard errors more than the betas, the effect estimates. If you're looking at predictors which change within subjects, like time, standard errors will go down. That's to your benefit. But if you're looking at predictors which compare subjects to each other, like gender, the standard errors will probably go up. Your power calculations must take account of the correlation. That's that factor D, the study design factor, and you'll end up with an effective sample size based on D. And the analysis program you use must take account of the correlation. That's what we're going to talk about next week. And in order to run that analysis, you just have to make sure that your database is organized in this long format. Then your software will take it. And the rest will be done internally in terms of your analysis. And the actual results, you'll have beta, standard errors, p-values, just like always. So interpretation will be simple and straightforward. But getting to that point just involves this bit of complication in between. And sorry for taking so long, but please, if you still have questions, please ask.
Wonderful. Thank you so much. I'm going to open it to question, John. Can you hear me?
Yes, I can, perfectly.
Wonderful.
Should I take the slides off?
No, why don't you keep them, because we may go back to a couple. If I could start with one question. There was the slide where you defined D, the design, and there was a couple of slides down, or maybe the one next to it, after it, was the power and the sample size. Can we go back to that?
Yes.
Okay.
Can you see this?
Yes.
I'll do it from here if you don't mind. It's smaller but easier to move. So that's the definition of D, the design effect.
Right. Now, where are these sigma? I'm sorry, go back for a second. These.
Yep.
Okay, these between and within sigmas. Where did we get them from?
Good question. Do you have a pilot study?
We could, yeah.
That would be where I'd get them.
Okay.
So if you could do even 5-10 patients where you measure people, let's say twice. So I don't need a full-blown study, but if you can measure people on the same sort of time schedule, so say baseline, their first measurement, and then 6 months later, give me 5-10 people like that. I can run an analysis that will give me the variability between and the variability within. From those two numbers, I can calculate the correlation. That will give me the design effect. And we'll be in business to design your ultimate study. Now I need enough people that I get a stable estimate. That's why I wanted you to do 10 or 15. I don't need enough people to solve your intervention. I just need enough to get an estimate here. And the correlation is going to depend on how far apart the measurements are. And so that's why I asked you to measure them today and in 6 months. If you measure them today and tomorrow, you're going to get a very high correlation. If you measure them today and a year from now, you're going to get a very low correlation. So I need the timing to be the same as it will be in your ultimate study, if I'm going to get the right value for the correlation.
But assuming we have 10 subjects measured twice over 6 months, what actual formula are you using to derive the sigmas? I'm not able to visualize that in my head.
Yep, that's because you can't. Remember I said next week we're going to talk about the analysis that deals with all these things correctly?
Okay.
That same program, if you just feed in those 10 patients with 2 measurements each, it will put at the top the sigma squared within and the sigma squared between.
All right.
And then you just need to add and divide.
Okay, great. Can we
So there is no single program in Stata or SAS or that I know that will give you this single number. You're going to have to do the 2 pieces separately.
Sure. Can we go to the next one?
Yep.
Okay, and the next one? Okay, and so there was one that had power and sample size. Maybe it's further down.
Oh, the instructions, sort of.
Yeah, sorry.
Nope. Yep, this one?
Yes.
Okay.
I personally thought it was a bit too fast for me to grasp. So can we just go over these couple of slides if you don't mind?
I'm happy to do it. This one though? Or
yeah, this
from
one
earlier?
Yeah, this one.
Okay.
Yeah.
Okay. Do you mind actually giving me, it'll be easier, more concrete if you can give me an example. What would you like to do in your longitudinal study?
So I'm going to measure blood pressure actually at 0, 6, and 12, but let's take 0, 6 if you want. Which actually, this is the pilot we talked, well, this is the data set we talked about that we could use for the further modules.
Yep. And we're going to do a sample size calculation to detect whether there are changes in blood pressure, or do you have 2 groups that you want to compare?
I have 2 treatment groups, and I have 2 gender. But let's say I have 2 treatment groups given different doses of medication, and I'm measuring blood pressure at 0, pre-intervention, 6 and 12 months. And I'm trying to figure out if there is a treatment effect, so it's a between subject effect over time.
Good. What I would like you to do is a usual sample size calculation. Okay. So you're going to go to your software program or your sample size formula for doing a t-test, comparing mean blood pressure in one group to the mean blood pressure in another group. So to do that, you're going to have to specify how big the intervention effect is.
Sure.
So the difference in average blood pressures. You're going to have to specify the variability in blood pressure measurements, the standard deviation. You're going to specify what the power is, and I assume you're going to use a type 1 error of 5%. So all the usual inputs.
But do you use the last time points or the mid time point? Like we have 0, 6, and 12, right? So it depends on what my primary outcome is, right?
Yes. Now we're getting complicated.
We can
well,
it.
now see it's the beauty and the good and the bad of a longitudinal design. If you have 0, 6, and 12, what I could do is compare across 6 and 12. So the average of all the blood pressures at 6 and 12 months in the intervention group to the average of the blood pressures at 6 and 12 months in the control group. You're getting sort of like twice the sample size. But I'm assuming that whatever you've accomplished is now consistent. So if there's a benefit at 6 months, there's also the same benefit at 12 months. How does that sound to you scientifically?
That sounds good.
That sounds reasonable?
Yeah.
You don't think that the benefit is progressive?
Well, I mean, I think it's a good start.
I'd
We could
rather you said
explore
no.
both. Well, I know you do that, and actually, it does get better as we go on with time. But I think a more
Okay.
conservative look would be this is a good estimate.
Okay, good. Then 6 and 12 months, my K is actually going to be 2. The baseline won't help me here because there's no difference. I presume the groups start at the same time with nothing.
Correct.
So K is 2. Keep that in the back of your mind. How big is the difference? You can call it 6 months or 12 months since we decided it's the same difference at each. How big is the difference between the two groups?
I can't recall, but I would say 4 millimeter, and the standard deviation was around the same size. 4
Okay,
millimeter
good.
mercury.
Yeah,
I could be
mean,
off by numbers.
Yeah, no, numbers don't matter. It's just so I have something to talk about. So the difference is 4 between the groups. If you looked at a formula, that would be the mu1 minus mu2.
Right.
The standard deviation is 4. That's the S that shows up in the formula, or if it's a software package, they always ask for the standard deviation.
Sure.
You will need to tell me what the power is that you want.
Let's say 80.
80% power, that translates into something the software knows how to do. And what sort of type 1 error, false positive rate, can you tolerate?
Let's do the usual 5%.
5. Good. I just took those numbers, and since you made up numbers, so did I. You will need 90 people in each arm of the study. I just made that up. But that I could get from a standard textbook formula or a standard software program. It'll tell me that I need 90 independent measurements per group.
Okay. But when you entered it in the software, you use the correlated measure or the independent?
No. I just used the numbers you told me. 4 for the mean difference, S of 4, 80% power, alpha of 0.05.
Yeah.
I didn't tell the program that they were correlated because most programs don't allow that.
Okay.
And most formulas you look up in a book don't allow that. So that's what I say, that you're going to use a standard, your usual software formula to calculate the necessary sample size.
Okay. All right. So you entered.
And once
So you entered the correlation through your D design formula, but after that it doesn't appear?
Correct.
Okay, got it. Okay. Thank you.
Okay, so should we finish this example?
Sure.
Okay, so now I need D. We decided we're going to use the 6 and 12 months, so K is 2. D is equal to 1 plus K minus 1. That's 1 times the correlation. So 6 months apart, how strong do you think the correlation is going to be?
I think 0.5 was fair. I don't recall exactly, but I think it's close enough.
Okay, so that'll be 1 plus 1 times 0.5. D is 1.5. Okay.
Okay.
Now I just need to take 90 times 1.5, which is 135.
Okay. Perfect.
And no, it's 135 measurements per group. But each person has 2 measurements, so 135 divided by 2 is 70, no, not quite 70, 60.
67.5.
Thank you. 67.5 people, call it 68 per group.
Okay. Perfect.
So instead of having to have 90 people per group measured once, you can get by with 68 people per group measured at 6 and 12 months.
That's very helpful.
Good. Yeah, you need sort of to do this. But D is sort of the factor that you apply. It may be that you can find software formulas that incorporate it for you, but I've been hard pressed to find that. So I always end up just doing it myself.
Thank you so much. That really illustrates the point, because
Sure.
I wasn't able to comprehend how you use the usual formula for power, and yet it's correlated measure. Thank you.
Yep.
Any other questions? All right, I guess there will be no other questions. We're going to be posting those on the SHARP website if you don't mind, and we look forward
Absolutely
for
fine.
part 2.
Okay.
And thank you so much for the time and the insight. Thanks a lot, John.
Okay, you're welcome. If there are comments, feedback, I have time to make adjustments before the next lecture. So please, if things were unclear, too fast, too slow, please let me know before next week.
Thank you so much. Have a good
You're
day.
welcome.
Thanks.
Always.